Hello, we're back again. So today we want to talk about increments and differentials, and you will find this material in your textbook starting on page 156. So as a starting point, let's consider a function y equal f of x, and just suppose that it looks like this graph that I've got sketched here. I think we know that an increment of x, just a little chunk of x, is often written as delta x. And we can talk about a change in y as being delta y. Now let me start illustrating here by putting a value x1 on this horizontal axis. And then let's get another point, x2, and suppose that we designate x2 as x1 plus a tiny chunk of the x-axis, delta x. So x2 is just x1 and then move ahead an amount delta x. Now I'm drawing this as though delta x were positive, and in most illustrations it is, but there's no reason why it couldn't be negative as well. And we could be talking about moving backwards here a little bit on this axis, but we'll just keep this one drawing and keep things simple. So delta x is just I'm going to say just a bit of the x-axis. Now delta y would be the change in y as x moves from x1 to x2. Delta y would be the change in y. So that change I could write as f of x1 plus delta x minus f of x1. And that tells me that delta x is independent. It's just a piece of the x-axis. But delta y is a little more complicated. Delta y is a function of the x1 that we pick, the size of the delta x that we pick, and the function that we're talking about. So the change in y, if I move an amount delta x, if I move that amount right here, then the change in y, and you can see that I'm indicating spots on the graph. I think I'll change color again. Then the change in y is I would move from x1 to x2 would be this amount right here. That would be an amount delta y, the change in y. But if I would move the same amount delta x over in this region, over in here somewhere, then delta y, because the curve gets steeper, delta y would be much bigger. So delta y is a function of three things: the x1 that we pick, how far we move, the delta x, and what the particular function is that we're playing with right now. So as an example, if we had y is equal to 2x squared minus 6, and if we would let x1 equal 1 and delta x equal 2, then x2 would be x1 plus delta x would be equal to 3. Now I'll tell you right now, this would be an unusually large value for delta x. In practice, delta x, for the kind of problems that we're going to use differentials for, delta x would not be this big. But this is just fine for illustration. Then we would say that delta x is equal to you can find it as x2 minus x1 would be 3 minus 1 equals 2. In this case, delta x was already written down, but if it wasn't, we could find it if we knew x1 and x2. And delta y would be f of x2 minus f of x1 would be equal to, now we'll have to refer to what f is, and in this example we've taken our function to be that value right there. So this would be 2, 3 squared minus 6, I'm going to put that in parentheses, minus f of x1 would be 2, 1 squared minus 6 would be equal to 3 squared is 9. So 2 times 9 is 18. 18 minus 6 is 12. Minus 1 squared is 1 times 2 is 2. Minus 6 would be negative 4, but I got a negative out here in front. So that would be minus a negative 4 would be the same as adding 4 would be equal to 16. And so that's what the change in y would be. Now that is work with increments. Let me get some more paper here. Sometimes it's just inconvenient to find the increment. If I've got a complicated function, it may be a little bit inconvenient to find the increment delta y. But we can find something called a differential that's usually easier to find, and it's approximately the same as delta y. Now, what is the differential? Well, actually we have two differentials. We have a differential that we designate dx, but that differential is just an increment along the x-axis, and so that increment is exactly the same notion as delta x. But we have another differential called dy, and that one's a bit different. So what to do here? I think what I'll do is draw a sketch and see if I can give you the definition of dy in a manner that you'll have no trouble remembering. So let's just sketch a convenient y equal f of x function here, and let's take a point x1 and a point x1 plus delta x, x1 plus delta x, and I know that this would be f of x1. Now, if we would think about the tangent line to f at that point x1, let me see if I can sketch it. There's a trick I can use here, maybe. Get a straight line that goes through there. So that would be the tangent line, and the slope of that line would be f prime x1. That would be the slope of this line. Now consider with me for a second, and I think I'll change color again because I've got lots of colors. I want to consider, just come over here horizontally like that, and then consider this distance right in here. That little distance there. And let's call that, because we don't have a name for it right now, let's just call it by the Greek letter delta. So what do we know about delta? Well, delta is the difference between this horizontal line and the tangent line. So if we would remember that f prime at x1 is the slope of the tangent at x1, then f prime x1 would be equal to, going back to some earlier math in an algebra course, the rise over the run would be equal to, well, now the rise, and remember, it doesn't matter if we're talking about a straight line, we can calculate the slope of the straight line given any 2 points. So this point and this point would do as well as any other 2 points. In this case, the rise would be this little delta that we've defined in the picture. So we'll put a delta in there. And the run would be from here to here. So that run would be delta x. And we know that delta x, we know from this definition right here, that delta x and dx are the same, and so delta over dx would be f prime x1, or we could say that f prime x1 dx is equal to this little delta thing. That would be this distance right here. Now that distance is what we mean by the differential dy. So now you don't have to call that delta, you can call it dy. And let's look at this one addition. I'm going to draw a horizontal line through here and note this distance from here down to here. That distance, that's the real change in y. This distance right in here, this is going to be offset just a little bit. That distance is delta y, and this distance is dy. And they're not the same, but they're close to the same. And I think you can also appreciate if delta x is smaller, then this point would be moving back in this direction, and the difference between dy and delta y would be even less. So dy is equal to, this is by definition, f prime x dx. Now let us work an example. Let's suppose that f of x is equal to the square root of x plus 3, and that we want an x equal to 4 and a dx equal to 0.1. And then the directions are to find delta y and dy. Now neither of those will be very hard to find in this instance, but that's good. Things don't have to be hard all the time. So maybe let's do delta y first. So delta y would be f of x1 plus delta x minus f of x1. You see, because x is given as 4 and dx is given as 0.1, and dx and delta x are the same thing. All right, so what would this be? This would be the square root of 4.1 plus 3 minus the square root of 4 plus 3 is equal to, and I used my calculator a while ago, and I think this is equal to 0.0248. It would be worth your while to double check me on that. Just get out your calculator. So what does that tell me? That tells me if x moves from 4 to 4.1, then the y will change by an amount of 0.0248. So if x changes from 4 to 4.1, so x moves an amount 0.1, then y will move an amount 0.0248. Now what about dy? Well, dy would be f prime x dx, and so we're going to need to find out what f prime is before we can go further with that. So we'll do a change here of color again. So I'm going to rewrite f as f of x is equal to x to the 1/2 plus 3. I suggested in earlier videos that you use fractional exponents, and it makes taking derivatives easier. F prime x then would be equal to, what's our rule? This is just a power function. It's x to a variable, to a value. So we'd bring down the 1/2, write the x, and reduce the exponent by 1. So if I subtract 1 from 1/2, I get negative 1/2. And if I'm so inclined, I can write that as 1 over 2 times the square root of x. So there's f prime. And then dy would be f prime evaluated at 4 times dx, which is 0.1 in this case, would be equal to 1 over 2 square root of 2 times 0.1. Oh, I jumped the gun here a little bit. I extracted the root already, and what the independent variable is 4, so this would be over 4. Now let's do the arithmetic. Now you take the square root of 4, you get 2, multiplied by 2, you get 4. This is 1 over 4, or 0.25, multiplied by 0.1, and you get 0.025. So what have we found? We found dy is equal to 0.025, and we found that delta y is equal to 0.0248. Well, they're not identical, and we didn't think they would be, but they're pretty close. Now, I'm going to try to hold this video lesson to 20 minutes. So what I'm going to do is to work problem 50. And do I have enough room here? I think I'm going to get a new page of paper. So let me clear this. And I want to read the problem to you. Problem 50 is on page 162. On page 162. And it reads thusly. An egg of a particular bird is nearly spherical if the radius to the inside of the shell is 5 millimeters and the radius to the outside of the shell is 5.3 millimeters. Approximate the volume of the shell. Now that sounds like an intriguing problem. So let's build a sketch here, and I'll try to make that as near a circle as I can. and I'm exaggerating the thickness in comparison to the size of the egg for emphasis, but it says that the radius to the inside of that shell is 5 millimeters, and I'll just put a 5 here to remind us of that. And the radius to the outside of the shell is 10 millimeters. So we want to know about the volume of the shell, just the shell volume, just the shell, not the material inside, but how much material it took to build that shell. So what do we know? Well, we know that a volume of a sphere is equal to 4/3 pi r cubed. So that's the formula for volume. And we know that we would want to find, but I'm going to say approximate delta V, the change in volume, as my radius goes from 5, and this wasn't 10. It was, I don't know why I wrote 10 there. This was, in fact, now my colors don't match, 5.3. Okay, so we want to approximate delta V as R changes, R equal 5.0 to R equal 5.3. And we're going to approximate with dV. Delta V will be approximately the same as dV would be equal to V prime R dr. And we know that the R we start with is equal to 5 millimeters. And the delta R, how much did R change? It went from 5 to 5.3 millimeters. And so the delta R is 0.3, and those units are millimeters. And if we can find V prime, and you know, I think we can do that. If we can find V prime, we've reduced this to just an arithmetic problem. So V prime is going to be equal to, just using the laws that we know for taking derivatives, 4/3 pi, those are all constants, and so that would be the coefficient of R cubed. Now take the derivative of R cubed would be 3R squared, and these 3's can cancel out, and so this would be 4 pi R squared. So that's what V prime is. So now we can fill in here, and instead of symbolically having V prime, we can say 4 pi, R is 5 squared, and then times the dr, and the dr is delta R, of course, is equal to dr, because R is the independent variable. The delta and the dr are the same, so this would be a 0.3. So what do we have here? We've got 25 times 4 is 100, so it's 100 times 0.3 would be 30, so it's 30 pi. And because it's interesting to know things like this, I multiplied that out for you, and that is 94.25 cubic millimeters. 94.25 cubic millimeters. That's how much material is in that shell. So that is material out of your textbook, and you're going to have to read your textbook, of course. Feel free to ask me questions, and problems, as always, are going to be posted in My Open Math. So you'll find your new assignment in My Open Math and the due dates, and get in there, keep studying, and please feel free to ask me questions. And have a good day.